Hey everyone, today we're going to be talking about indefinite integrals and the antiderivative. Normally, given a function f of x, your goal is to find f prime of x. Now we're going to flip things around. Given a function f of x, we're going to find a function big F of x where the derivative of big F of x is equal to little f of x. Let's look at some examples. Consider the function f of x equals to 2x. Now I can define capital F1 of x as x squared. Certainly the derivative of x squared lands us at 2x, our original function. But that's just one possibility. If I define capital F2 of x as x squared plus 3 and capital F3 of x as x squared minus 4, well, it turns out that the derivatives of F2 and F3 also give us 2x, because the constant terms get killed off by the derivative. So if you want to cover all possibilities, let capital F of x equal to x squared plus c, where c is some arbitrary constant. It should be clear that the derivative of capital F of x will get us 2x, our original function. Next, consider g of x is equal to x cubed. If I define capital G1 of x as 1/4 x to the 4th, and capital G2 of x as 1/4 x to the 4th minus 3, then we can see that taking the derivative of both of these functions will land us at x cubed. Therefore, in a similar fashion to what I did previously, we can define capital G of x as equal to 1/4 x to the 4th plus c, where c is some arbitrary constant. So we'll go ahead and define the indefinite integral of a continuous function f of x as the family of functions such that the integral of f of x is equal to big F of x plus c. In other words, we're looking for a family of functions such that f prime of x is equal to f of x. Unlike the definite integral, this integral sign does not have upper nor lower bounds. You simply write the integral symbol without a sub or superscript. That's what's ultimately indicating that we are taking an indefinite integral. We'll go ahead and get the ball rolling by defining some integrals of power functions. First, if k is not equal to -1, then the integral of x to the k with respect to x is equal to x to the k plus 1 divided by k plus 1 plus some arbitrary constant c. Notice that if I took the derivative of the right-hand side, I would end up with x to the k. Now, in the case that k is equal to -1, then the integral of x to the k is equal to the integral of x to the minus 1, which is going to give us the natural log of the absolute value of x plus c. This one is a little bit strange, but we got to make sure that our exponent is equal to -1 to get this rule. Let's look at some examples. We'll first compute the integral of 3x squared dx. First, we'll factor out that 3, so we can recognize that we are taking the integral of a power function. Now, using rule A, we get that this is equal to 3 times x cubed divided by 3 plus c, which simplifies down to x cubed plus c. An easy trick with integration problems is to take the derivative of your answer. If you land back at your original function, then you know you've done it correctly. In our next example, we'll consider the integral of 3 over x plus 2x to the 4th. In our first step, we'll break the interval up to get 3 times the integral of 1 over x dx plus 2 times the integral of x to the 4th dx. Now we'll go ahead and use the rules above to get this is equal to 3 times the natural log of the absolute value of x plus 2x to the 5th divided by 5 plus c. Next, let's look at the integrals of some exponential functions. Our first rule states that if k is not equal to 0, then the integral of e to the kx dx is equal to e to the kx divided by k plus c. And then our second rule states that if b is strictly greater than 0 and b is not equal to 1, then the integral of b to the x is defined as b to the x divided by the natural log of b plus c. Now consider the following example. We'll take the integral of 4 times e to the 2x plus 3 dx. This doesn't quite look like a very user-friendly function, but let's use some tricks from algebra to break this up and to make it a little bit nicer. The first thing we can do is factor out this 4. but notice that we have e to the 2x plus 3. Now, we know from algebra that I can actually break this up as 4 times the integral of e to the 2x times e to the 3. Recall that if I have a sum in the exponent, I can split up the base and write it in the following way. Now, e to the 3 is also a constant, so I can factor that out as well. Thus, my original integral is now rewritten as 4 times e to the 3 times the integral of e to the 2x plus dx. Now, we can go ahead and use rule A above to find that this is going to equal to 4 times e to the third times the quantity e to the 2x divided by 2 plus c, which simplifies down to 2 times e to the third times e to the 2x plus c. And we're done. Next, we'll go ahead and display a list of 6 common trigonometric integrals. Now notice that this list is going backwards. On the right-hand side of each equation, we're getting our 6 common trigonometric expressions. Just pay attention to the signs in each one of these. Each integrand is positive, but in some of these, our answer happens to be negative. At the moment, we're not utilizing any tools to prove these statements, we're simply just taking them as fact. But we'll go ahead and move on to some examples. In our first example, consider the integral of 6 times cosine of 5x plus 1. We'll go ahead and factor out that 6 to focus on the more important part of this problem. This doesn't directly represent one of the formulas that's posted on the previous page. This one's a little bit more interesting. Here I'm taking cosine of 5x plus 1. Now what I'm going to do is have us think back to our days using the chain rule. If I was taking the derivative of a function that looks something like this, I would notice that the derivative of the inside quantity, 5x plus 1, comes out to 5. So if I am trying to find this antiderivative, I have to make up for this missing factor of 5. So since d dx of 5x plus 1 is equal to 5, then the integral of this quantity will equal to 6 times 1/5 times sine of 5x plus 1. The sine comes from the fact that we are integrating cosine. That shows up on the previous slide, but this addition of the factor of 1/5 here, that one's a little bit tricky. Again, think about what happens if I were to take the derivative of sine of 5x plus 1. Well, the chain rule would produce this factor of 5, and since that is not present in our original problem, I have to put in a factor of 1/5 to make up for that missing factor of 5. Think about it this way. If I were to take the derivative of sine of 5x plus 1, I would end up with 5 times cosine of 5x plus 1. So this factor of 1/5 makes up for that missing factor of 5. This problem is basically the chain rule, but in reverse. And of course, once I simplify everything, I'll end up with 6/5 times sine of 5x plus 1 plus c, and we're done. In our next example, consider the integral of tangent of x plus x times secant squared of x dx. Now, the thing to notice automatically about this is I don't have a formula for tangent of x. So what are we going to do about this? Well, I'm going to make 2 observations here. The first observation is that the derivative of tangent of x is equal to secant squared of x, which is a present term in my integrand. Also, the derivative of x is equal to 1, which is also a factor of tangent of x. So in a manner of speaking, we're looking at the product rule, but in reverse. So thinking about the product rule, if I'm looking at tangent of x plus x times secant squared of x, then it seems that I can put this all together and realize that this all came from x times tangent of x. If I were to take the derivative of x times tangent of x, then the product rule would give me tangent of x plus x times secant squared of x. So in a similar way to how problem 1 was the chain rule but almost in reverse, problem 2 is essentially the product rule but in reverse. Let's look at a couple more examples. Consider the integral of -7 times cosecant of x over 3 times cotangent of x over 3 dx. I'm going to go ahead and factor out that 7 and do a similar trick that I did in example 1 on the previous page. I'm taking cosecant and cotangent of stuff. Now the derivative of this, in other words the derivative of x over 3, is going to be equal to 1/3. Now, similar to how we did in the previous example, we need to add in the inverse of 1/3, which is 3, to compensate for the loss of this. Again, this is like the chain rule in reverse. Notice that if I took the derivative of 3 times cosecant of x over 3, I would still end up with minus cosecant x over 3. Therefore, my final answer becomes 7/3 cosecant of x over 3 plus c. And in our last example, let's consider the integral of tangent squared of x minus secant squared of x. Now this one's a little weird because even though we have a formula for secant squared of x, we don't have an integral formula for tangent squared of x. So the question is, what do we do about that? Well, recall the trigonometric identity known as one of our Pythagorean identities. Tangent squared of x plus 1 is equal to secant squared of x. So let's use this to our advantage. Subtract secant squared of x from both sides and subtract 1 from both sides. This will allow us to make the following substitution. We can replace tangent squared of x minus secant squared of x with negative 1. Then we're just integrating negative 1, which will give us a final answer of negative x plus c, and we're done. Solving this particular interval came down to knowing some helpful trig identities.